The chameleon is said to vanish into any background. In reality, its colors are not a cloak of invisibility, but a language written in light, tension, and living crystal. In the forests of Madagascar and the dry scrublands of Africa, chameleons move with deliberate precision. Their changing colors seem magical, yet the science behind them reveals a far more complex story. The popular belief that chameleons change color to blend seamlessly into their surroundings is widespread, but scientifically incomplete. While camouflage can occur, it is rarely the primary function of their color shifts. In most species, baseline coloration already matches the natural environment, greens and browns suited to forest canopies and shrublands. The dramatic transformations often seen in documentaries or viral videos are typically responses to social or physiological stimuli rather than background matching. Research on species such as the veiled chameleon, Chamaeleo calyptratus, and the panther chameleon, Furcifer pardalis, demonstrates that color change correlates strongly with emotional state, dominance interactions, and reproductive signaling. Males encountering rivals intensify their hues, bright yellows, reds, and blues, making themselves more conspicuous rather than less visible. During courtship, similarly vivid displays are used to attract females. If concealment were the primary objective, increasing brightness and contrast would be counterproductive. Instead, these displays serve as visual signals in dense habitats where clear communication can reduce the need for physical conflict. Thus, the chameleon's palette evolved less for invisibility and more for expression. Unlike animals that rely mainly on pigment dispersion, chameleons employ a sophisticated nanocrystal-based system embedded within specialized skin cells called iridophores. Beneath the upper pigment-containing chromatophores lies a lattice of guanine nanocrystals arranged in a precise three-dimensional pattern. When a chameleon is calm, these nanocrystals are tightly packed, reflecting shorter wavelengths of light, primarily blues and greens. When excited or stressed, muscular contractions alter the spacing between the nanocrystals. Increased spacing shifts reflected wavelengths toward longer frequencies, producing yellows, oranges, and reds. This mechanism was detailed in a 2015 study published in Nature Communications, which demonstrated that panther chameleons can actively tune structural coloration through mechanical changes in the skin. The process is rapid, reversible, and energetically efficient. Pigments still play a role. Xanthophores and iridophores contribute yellow and red tones, while melanophores influence brightness and contrast by dispersing or aggregating melanin granules. However, the structural layer beneath them provides the dynamic optical foundation. This layered system allows for extraordinary chromatic range without synthesizing new pigments in real time. It is a case of evolutionary innovation at the nanoscale. Color change in chameleons functions primarily as a language. Territorial males display intense color contrasts to assert dominance. The brighter and more saturated the display, the more likely a rival is to retreat without physical combat. In controlled observations, males with more vivid color responses often win confrontations, suggesting that color intensity signals physical condition. Females also use coloration to indicate reproductive status. In several species, gravid females adopt darkened backgrounds with contrasting spots or bands to signal non-receptivity, discouraging further mating attempts. This reduces unnecessary stress and energy expenditure. Stress responses likewise influence coloration. A threatened chameleon may darken overall, increasing melanin concentration to absorb more heat or signal distress. Thermal regulation is intertwined with this system. Darker colors absorb more solar radiation, enabling faster warming during cool mornings, particularly in montane habitats where temperatures fluctuate sharply. Thus, color change operates at the intersection of behavior, physiology, and environmental adaptation. Color signaling would be ineffective without the visual acuity to perceive it. Chameleons possess some of the most distinctive eyes among vertebrates. Each eye moves independently, capable of nearly 180-degree rotation. This grants a combined field of view approaching 360 degrees. Their retinas contain both rods and multiple classes of cones, allowing detection of a broad range of wavelengths, including ultraviolet light. This expanded visual spectrum enhances their ability to interpret subtle color cues during social interactions. When prey is detected, typically insects at distances up to twice their body length, the eyes converge for stereoscopic precision. The ballistic tongue, powered by elastic recoil mechanisms, can extend in less than 0.07 seconds and reach lengths exceeding the animal's body length in some species. This extraordinary visual motor coordination complements their color-based communication. The same sensory sophistication that allows them to track prey also enables them to read the chromatic signals of rivals and mates. There are more than 200 recognized chameleon species, with the majority inhabiting Madagascar. Others range across sub-Saharan Africa, parts of southern Europe, and regions of the Middle East and South Asia. Species vary dramatically in size, from the tiny Bruchisia micra, measuring under 30 mm in total length, to the Parsons chameleon, Calumma personii, which can exceed 60 cm. Not all species exhibit dramatic color change. Some smaller, leaf-litter-dwelling species rely more heavily on static camouflage and subtle tonal adjustments. Arboreal species, particularly those engaged in active territorial behavior, display the most pronounced chromatic shifts. Habitat structure influences signaling strategies. In dense forest canopies where filtered light creates complex backgrounds, high-contrast displays ensure visibility to intended receivers. In open or arid habitats, color shifts may be more muted. Climate change and habitat loss increasingly threaten several species. Because color regulation is tied to temperature and stress physiology, environmental disruption can have cascading effects on behavior and reproduction. Understanding the true function of color change is therefore essential not only for correcting a misconception, but for informing conservation strategies. The myth of camouflage oversimplifies a system that is far more intricate. Chameleons do not vanish into their environment at will. Instead, they broadcast information about strength, mood, readiness, and survival, through a dynamic interplay of light and structure. Thank you for watching. Subscribe for more evidence-based explorations of the natural world, where familiar creatures often conceal deeper truths.